It was just before midnight on March 12, 1928. The St. Francis Dam stood in San Francisquito Canyon, holding back a reservoir filled almost to capacity. Only hours earlier, Chief Engineer William Mulholland had personally inspected reports of leakage around the dam. He and his assistant examined the structure and its abutments. They saw seepage, but they did not consider the dam to be in immediate danger. Then, at approximately 11:57 p.m., the dam failed. Not gradually, not with hours of warning. The concrete structure was suddenly destroyed, releasing an enormous volume of water into the canyon below. The flood surged through San Francisquito Canyon. Water, mud, trees, and boulders raced downstream toward the Santa Clara River Valley. The wave eventually reached the Pacific Ocean. More than 450 people were killed, according to California's modern historical accounting. But the most important question was not simply, why did the concrete fail? Investigators eventually discovered that the answer was buried beneath it, in the ground, in the geology. The dam had been placed across a foundation containing weak, fractured rock and an ancient landslide zone, and once water entered that system, the foundation itself became part of the failure. This is the story of how a dam designed to control water was ultimately defeated by the ground beneath it. The St. Francis Dam was built as part of the Los Angeles water system. It was intended to provide additional storage for the Los Angeles Aqueduct. Construction began in 1924. The dam was completed in 1926. At maximum reservoir level, it stood roughly 200 feet high and stored approximately 38,000 acre-feet of water. But the project evolved during construction. The dam was raised beyond its original planned height to increase storage capacity. The concrete mass was enlarged vertically, but the resulting structure did not receive the kind of foundation drainage and inspection provisions that later dam engineering would consider essential. There was no inspection gallery. The foundation was not pressure grouted, and drainage beneath the dam was limited to part of the structure. The result was a massive concrete barrier depending heavily on the quality of the rock supporting it. That distinction matters because concrete can be extremely strong, but a dam is only as reliable as the foundation transferring its enormous loads into the earth. And at St. Francis, the foundation was anything but simple. The dam crossed a geological contact between two very different rock formations. On one side was Pelona schist. The rock was foliated and fractured, with its planes generally dipping toward the canyon. More importantly, parts of the foundation were associated with an ancient landslide mass. The dam was placed across a known fault zone. The problem was not simply that the rock was weak. The problem was how the rock behaved when water entered it. Along the schist, existing fractures and slide surfaces could provide pathways for water infiltration. Water reduced the stability of already fractured material. And on the opposite side, another problem appeared. The western foundation contained red conglomerate. This rock included gypsum. Gypsum is calcium sulfate dihydrate, CaSO 4 times 2H2O. And when gypsum-bearing material becomes saturated, gypsum can dissolve. This is the critical mechanism. The reservoir was not simply pressing against a concrete wall. Water was also penetrating the geological system beneath and around that wall. The rock was becoming weaker, seepage increased, foundation material could soften and deform, and water pressure began acting through pathways that the original design did not adequately control. During the final filling period, significant seepage developed around the foundation. By the afternoon before the collapse, reported discharge in the area had increased substantially. Then, just before midnight, the geological system could no longer support the structure. The failure began at the foundation, not at the top of the dam, not in the reservoir, but underneath the concrete. A dam experiences enormous forces even when everything is functioning normally. The reservoir pushes horizontally against the upstream face. The dam's own weight pushes downward, and water entering the foundation can create uplift pressure beneath the structure. At St. Francis, inadequate foundation drainage meant those pressures could not be effectively relieved throughout the entire dam. As the western foundation weakened, support beneath the dam was compromised. The structure began to lose the stable foundation it depended upon. The failure then propagated through the dam and its abutments. Historical investigations concluded that softened foundation material beneath the western section contributed to the initial failure, followed by collapse of the eastern section as the remaining structure lost support. At approximately 11:57 p.m., the reservoir began escaping through the shattered structure. The reservoir contained roughly 38,000 acre-feet of water. That is approximately 12.4 billion gallons. The concrete had failed. The foundation had failed. And now gravity took over. The released water accelerated down San Francisquito Canyon. It carried mud, trees, boulders, concrete fragments, and enormous quantities of debris. The flood entered the Santa Clara River Valley and continued toward the Pacific. Its destructive path stretched for roughly 70 miles. California's historical record describes a swath approximately 2 miles wide through portions of the valley. Hundreds of homes, bridges, roads, farmland, and other infrastructure were destroyed. More than 450 people lost their lives. The disaster became one of the deadliest failures in California history. The scale of the destruction was enormous, but the initiating mechanism was remarkably simple. Water entered the foundation. The foundation weakened, the structure lost support, and an entire reservoir was released in minutes. The St. Francis Dam did not fail because concrete was incapable of holding water. It failed because engineering decisions were made without fully understanding the geological system beneath the structure. The dam was enormous, the reservoir was enormous, but the critical weakness was underground. William Mulholland accepted responsibility for the disaster and resigned from his positions. His career as Los Angeles's dominant water engineer effectively ended. But the consequences went far beyond one engineer. California changed its approach to dam safety. In 1929, the state created a formal dam safety program in direct response to the St. Francis failure. Its responsibilities included reviewing dams, approving plans for new and existing structures, supervising construction, and overseeing maintenance. The lesson was not simply build stronger concrete. It was understand the ground. A dam interacts with water, water interacts with rock, rock interacts with fractures, faults, pressure, and time. And when those systems are connected, ignoring one part can compromise everything above it. The St. Francis Dam was a monument to engineering ambition, but its failure demonstrated something every major infrastructure project must remember. You cannot engineer your way around geology you do not understand. That is the anatomy of disaster, not one spectacular mistake, but a chain of assumptions until water, pressure, rock, and gravity make every weakness matter.